Welcome back. So now let's use what we just did in video 1, which is linked in the description. We found the LU factorization of this matrix 1, 2, 3, 4. Now let's review how to use this. So when you have a system, you can say AX equals B in vector form. Okay, so it's a matrix equation, X is a vector, B is a vector. Then that means X, the vector, is equal to A inverse times B. But now remember that the whole point of this is to say X, the vector, equals, and A is equal to L times U. So you can say LU here times B, but this is the inverse of that, the -1 up there. So now you can say X as a vector equals, and then you apply the rule that says you gotta flip the order. So you're gonna have U to the negative first, which remember means U inverse, and then L to the negative first, which again really is L inverse, right? It's not to the negative first. And then B. Now we make the following substitution. We say the vector y is equal to whatever we get from doing L inverse B. But that says equivalently that you can say L times the vector y is equal to the vector B. It means the same thing. So this is modeled on something like saying x equals, what do you want to say, 2 to the negative first times, for example, 3. Which would be like saying, in other words, that 2 times x equals positive 3. You see, it's the same logic. But now we can say, because y is equal to L inverse B, that the vector x is equal to U inverse multiplying the vector y. But again, going by this simple principle right here, it's based on that pretty much logically. So you're going to have U times the vector x equals the vector y. So here are the key equations in this process that we have to know essentially. One is the following, that L, so the lower triangular times the vector y, like that has to be equal to the vector b that's given. The upper triangular matrix times the vector x has to be equal to the vector y. Those are our key equations. So to use them here, that means the following. And obviously, I get it. This is a 2x2 matrix example. It's not even really necessary, but that's not the point. The point is to try to understand things. So, in other words, imagine we have 1, 2, 3, 4 times some vector x, y. This is equal to, for example, some vector like -1 and then 3. All right, so let's work through this and see what happens. So in our case, first of all, so to relate this to our key equations, you take your lower triangular matrix, which you saw previously was the 1, 0, 3, 1. So you take this 1, 0, 3, 1, and you multiply it by this vector y, which is not known. So you call it, for example, y1 or ab. It doesn't matter. Just invent some things that you put in here, okay? It doesn't matter. y1, y2. And you want this to be equal to the vector at first, -1 and 3. So why do this extra step? Because from here, it's pretty straightforward to tell that 1 times y sub 1 plus 0 times y sub 2 equals -1. In other words, you can tell that like this, y sub 1 has to be equal to -1, you see? Now I can say 3 times y sub 1 plus 1 times y sub 2 equals +3. So dot product the second row with the column vector, set it equal to the 3, because that's what it would generate. And then y sub 1 is -1, so you're going to put 3 times -1 plus y sub 2 equals 3. So you're going to have -3 plus y sub 2 is equal to 3. So y sub 2 is equal to 6. Use the second equation that says that ux equals y. But again, it's going to be pretty easy because u is upper triangular. You can read off a value very easily. What I mean is this, take your u, which we found to be the following matrix previously, 1, 2, and then 0, and then -2. That row has only a single entry in it. Multiply this by the vector, so you're going to have x1 and x2. This has to be equal to y. But we know what y is, we just found it. It's equal to -1 and also 6. But from the bottom row, because this is 0, you can do 0 times x1, which is 0, -2 times x2 equals 6. You see, so -2x2 equals 6. That's easy. That means x2 equals 6 divided by -2, but that's -3. Once you know that, then use the top row. So you're going to have x1 plus 2 times x2. It has to be equal to -1. By the way, you do the dot product here, right? So 1 times x1 plus 2 times x2 equals the top entry -1. But now you know x2 is -3. So x1 plus 2 times -3 equals -1. So x1 minus 6 equals -1. So x1 equals -1 plus 6, which is +5. All right, so that means the following, in other words. Our system here has the following solution vector. X, the little arrow above it, is equal to 5, comma, and then be careful now. So -3. That solves the equation. I've done this for the case of a 2 by 2, but you can do this with a 3 by 3. The same logic applies, all relying on the fact that you want to have something like this, a row, like this red row here, because then, by the way matrix multiplication with vectors works, it's easy to get an equation like this, where you have a single variable that can be easily isolated. It kind of worked like that over here, also, right, where I'm highlighting in blue. A single variable easily isolated. Without that step, you got to set up and solve a system. It can be very complicated. The downside is, as we learned in video 1, you have to first figure out how to do your LU factorization, how to get these two matrices right here that I'm highlighting in gray. Those two matrices, which can be a lot of work unto itself. I'll see you in another video. Leave a like if it's helpful.